Hey everyone, welcome back to Calculus 2. This is lecture 29 of the course, and in this session we're going to discuss the power series. Okay, so we just got done discussing Taylor polynomials, and prior to that we discussed infinite series, and now we're going to take those ideas and we're going to combine them. Okay, so let's go ahead and jump into it. So we'll call this section 4.8 power series. Okay, so let's make sure we're focused here. Okay, all right, so previously we discussed approximating a function with a Taylor polynomial. I'll just say with Taylor polynomials. Okay. So the example we had at the time was f of x equals e to the x. So for that example, we said, the first degree polynomial, Taylor polynomial that approximated it at 0 was 1 plus x. Okay, and then we said, let's add the constraint that the second derivative be set equal to the second derivative of the Taylor polynomial at x equals 0. And we came up with a second degree polynomial that estimates it, and that was 1 plus x squared over 2 factorial. And we went on in this way to come up with a third degree, right? And eventually just kind of a general form where we said e to the x is approximately 1 plus x squared over 2 factorial plus ... plus x to the n over n factorial. Okay, so everything in between, right? N is a finite number, of course, but however many derivatives there happen to be, we can certainly crank out a Taylor polynomial for that. And e to the x is one of those functions that when you differentiate it, you get the same function back, and so we could in theory have an enormous number of these, right? And so then we said that the higher the degree, the better the approximation. Right? So the higher the degree of the polynomial, the better the approximation will be. So in this section, what we're going to do is we're going to introduce a power series which can be used to basically represent functions precisely, right? So no approximation, right? An actual equivalent power series that's actually equivalent to the functions representing. Okay, so let's go ahead and define that, and then we'll talk through what in the world it means, what it all means. Okay, so if x is a variable, right? Important to note that because this is going to be kind of a weird looking function. Then an infinite series of the form. It's going to be the sum from n equals 0 to infinity of a sub n x sub n, right? And that, of course, is going to be equal to a0 plus a1x plus a2x squared plus ... plus a sub n x sub n plus ... right? Of course, it's an infinite series. So an infinite series of this form is called a power series. Okay, now in this particular example, the power series is quote-unquote centered at 0. We can center a power series at any value c, and it has a similar form. So a power series centered at C has the form, it's a very similar form, right? But let's write it out. N equals 0 to infinity of a sub n x minus c to the n. Okay, so similar to the Taylor polynomials, right? So then a0 plus a1 times x minus c plus a2 times x minus c squared plus dot 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 plus a sub n x minus c to the n plus dot dot dot, right? So that's the more general form. So of course the first one is just where c is 0. Okay, now important to note, obviously, c is a real number, right? So I guess I should say that. All right, so any real number c. Right, so we're not allowing we're not allowed to center our power series at imaginary numbers, for example, like the square root of -1. Okay, all right. So this is the definition. So let's, we'll get into sort of like, what the heck is this in a sec. Let's take a look at an example of a couple of these things. All right, so an example. So the sum n equals 0 up to infinity of x to the nth power over n factorial. Well, this is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot, right? This is a power series. This is a power series centered at x equals 0, of course. Okay? And so, of course, this is the power series that's based on, the Taylor series we just looked at for the function f of x equals e to the x. We'll get into that connection in a moment, but you may be recognizing it. So another example is this. What about the sum from n equals 0 up to infinity of -1 to the nth power times x plus 1 to the nth power? So this is an alternating series. We clearly see that. And so this one looks like 1 minus x plus 1 squared minus, or plus, sorry, that's the first power, plus x plus 1 squared minus x plus 1 to the third power plus dot dot dot, right? It goes on forever. And so what is this power series centered on? This is a power series centered at x equals -1. Okay, very good. Okay, so let's keep in mind the structure of a power series is what it looks like. This it has the form n equals 0 to infinity of a to the n times x minus c to the n, right? So in our example, n equals 0 to infinity of -1 to the n times x plus 1 to the n, right? So the a of n in our case is this piece here. That's the a sub n. And then the c here is -1. Okay, right? So this is, you can think of this as x minus -1, otherwise known as x plus 1. Okay, right? So just keep that in mind. Keep in mind that that structure. And so a power series is an interesting thing. You can think of it as a function. So a power series in x can be viewed as a function of x, right? So you can think of it kind of like this: f of x equals the sum from n equals 0 to infinity of a of n, a sub n times x minus c to the n, right? So naturally you could plug in values for x. If I want to evaluate this power series at x equals 2, I could plug that 2 in to the entire function, right? Right. So for example, let's do an example like that. F of 2 would be equal to the sum from n equals 0 up to infinity of whatever a of n happens to be, and then 2 minus c raised to the nth power. Okay, so it's going to be some kind of like prefix on this, but then it's 2 minus wherever it's centered at raised to the nth power, right? You're going to get some number, right? And f of c, of course, would be what? It would look like this: n equals 0 to infinity of a sub n times c minus c to the nth power, and it's going to be equal to 0, isn't it? That power series will always be 0 if you evaluate it where it's centered, if you evaluate it at its center. Okay, so this kind of raises the question of what is the, if this is a function, if you can think of a particular power series as being a function, what's the domain of the function? Okay, the domain of f, we would say it's equal to the set of all x such that f of x is finite. Right, so what does that mean? Well, it's the set of all x such that the series converges when you plug in a particular x. Right, so I guess I should say i.e. the set of all x such that the series converges at when evaluated at x. Okay. All right. So an example of something that's always in the domain of any power series is C. All right. So C is always in the domain of any power series because the sum, well, so f of c is equal to the sum of a of n times quantity c minus c raised to the nth power. So this is always 0, right? So c is in the domain of f, always. Okay, so it's always in the domain of f, right? But what else can the domain look like? What else can the domain of a power series look like? Well, we have a theorem for that. Okay, and that theorem tells us that is going to tell us what the nature, what the nature of the domain of a power series is going to be, or can be, what the options are. So for a power series centered at C, one of the following is true. Okay, so first of all, the series could converge only at C. Right, so it's possible, right, that the power series would diverge everywhere when x is non-zero, or x is not C. Right, the trivial case would be where it's centered at 0. Right, so that's very possible. Right, so in that case, you would say the domain is a single point. Right, C, namely C. Okay, it's also possible that there's going to exist some R. The second possibility would be that there exists some R, a real number, right, such that the series converges absolutely for basically x minus c less than r, and would diverge outside of this. Whenever, well, for x minus c greater than r. Okay. All right, what does this mean, this x minus c less than r? Well, that just means that, if you're centered as c, then somewhere out here you'll have c plus r, and somewhere this other direction, you'll have c minus r. Right, so what are we talking about here? Well, we're talking about an interval. Okay, so this is an interval. So here, the domain is an interval, like a finite interval, right? R is a finite number, right? So it's some finite number. Okay, cool. That's interesting. And then the third option is that the series will converge everywhere. No, so for all x and r, right? And so in this case, the domain here is all real numbers. Okay, so that's totally possible as well, right? So it's one of these three. There's no alternative. So basically, what this means is it can't be. The domain of a power series is not going to be a series of intervals. It's not going to be isolated points scattered throughout the real numbers. It's not going to be, it's not going to be things like that. It's going to be a point, an interval, or everything. Okay. All right. That's cool. Very interesting. Right. So we're talking about stuff that's pretty new, probably. Right. So far we've said that we've defined what a power series is. Right, and we've said that we can think of it as a function. F of x equals the sum from n equals 0 up to infinity of a sub n x minus c to the nth power. Right, we can think of this as a function. The domain of the function is equal to the set of x such that f of x is finite. Right, that's not like any function you've likely seen before. Right, but in theory, in a lot of ways, it really is kind of the same idea of a domain as what you probably are used to. We would say the domain is all of the real numbers we can plug into the function sort of legally, right? And this is kind of a spin on that, right? This is in theory we can plug in any number into this sum, but we need to be sure that what we get out of it is a real number. Okay, so that's how functions normally operate, right? You plug something into a function. If it's in the domain, you get some real number out of the function. And so this is kind of the same idea. Okay, so a lot of what we'll talk about from starting now then is like how do we find the radius of convergence, and what even is it? Right? What does it mean? And so let's do an example where we try to find the radius of convergence. So let's find the radius of convergence of the following. So f of x equals the sum from n equals 0 to infinity of n factorial times x to the n. So this is a power series centered at 0. Okay, and so let's take a look at what happened. We already know, that the domain of any power series is going to contain C, right? So we would expect that f of 0 is 0, and let's just confirm that. Right, and that's going to be, so it'll be 0 factorial times 0 to the 0 power plus 1 factorial times 0 to the first power plus, and so on. We'll put 2 in there. 2 factorial times 0. This should be 0 to the second power, and so on, right? So you got a 0, a 0, a 0. So everything is 0, right? So obviously less than infinity, right? So this series converges at its center, as we would expect. All right. So let's take a look at where else it might converge. We know that it converges at its center. Let's talk about where else it might converge. So what we're gonna do here is we're gonna use some of the tests for convergence that we've seen up to this point in Calc 2. And so for this one, we're going to use the ratio test. Right, so remember, what we're looking at for the ratio test is we want to test that the limit as n goes to infinity of u of n plus 1 over u of n needs to be less than 1. Right? So the ratio test says that this is how this will have to work, right? So for our series, we will let u of n will be equal to n factorial times x to the n, and so that means u to the n plus 1 will be equal to n plus 1 factorial times x to the n plus 1 power. So then the limit as n goes to infinity of u sub n plus 1 over u sub n is going to be equal to the limit as n goes to infinity, and I'm just going to write these out in here, n plus 1 factorial times x to the n plus 1 over n factorial times x to the n. Right, and then what do we get here? We can do a lot of canceling. We get the limit as n goes to infinity of, what do we have? Well, it's still the absolute value, I suppose. We'll leave that in there for a second. N plus 1, and then you've got x to the n plus 1 over x to the n, so you just have an x there, don't you? Okay, and so this is technically equal to x times the limit. X, remember, x in this context is a constant. It's n that is increasing. So x times the limit as n goes to infinity of n plus 1. And what do we get there? Well, this is basically going to be x times, this is going to grow without bounds, so this is infinite. Okay, and so by the ratio test, right, so clearly this is going to diverge everywhere. Right, so you can see that. So the ratio test would say, hey, this is, the terms, the ratio of the n plus 1 term to the n term is diverges. And so that means that the series will diverge. And so what we can say here is that the series will diverge whenever the absolute value of x is greater than 0. So basically for any non-zero x. Okay? And so therefore, the radius of convergence is equal to 0. Right? So r is that radius. Okay? The radius of 0 is, the radius of convergence is 0. And so the domain of f would be equal to just 0 in this case. Okay, so a couple things you can say. Like, these are all kind of saying the same thing in a lot of ways. So let's try another one. So in this case, the domain is a single point, right? The power series converges. If you think of the power series as a function, this function, it converges just at its center. Everywhere else it diverges. Okay? So what about, let's try another example. And so this might be a slightly more interesting example. Let's find the radius of convergence of f of x equals the sum from n equals 0 up to infinity of 3 times x minus 2 to the nth power. Okay. So here we have, so this one doesn't have, this one is, you're successively raising a value to an exponent, an increasingly large exponent. So when will this converge? Right, so first of all, it's centered at c, it's centered at c equals 2. Right, so we know it converges at x equals 2. We could test this by plugging in a 2 for f, but you can see clearly that this will be 3 times 0 to the 0 power, 3 times 0 to the first power, 3 times 0 to the, right? So it's centered at c, so it converges at C equals 2. Okay. Now let's again use the ratio test here. Okay, so in this case, we're interested again in the limit as n goes to infinity of u to the n plus 1, or u sub n plus 1 over u sub n. All right, and we can just plug these values in. This would be the limit as n goes to infinity of 3 times x minus 2, and this would be the n plus 1 power over 3 times x minus 2 to the nth power. Okay, and so we can see some cancellation here. Right, the 3's will cancel, and pretty much all of the x minus 2's. I mean, this is the raised to the n plus 1 power, this is raised to the n power, so all but 1 will cancel. And so we're left with x minus 2, absolute value. Right, and so the the way to kind of think about it at this point is that this is less than 1 when what? Right, this will converge. Well, hold on. Let's think about a step back for a second. So when does this converge? This converges when it's less than 1. Okay, and so the limit here, this limit, is obviously just equal to x minus 2, right? Absolute value of x minus 2. Right, there's no n here, right? So this is just, the limit is this, is x minus 2 itself. And so this will converge whenever this piece here, x minus 2, is actually less than 1. Right, so this is usually the way that a power series that has an interval of convergence will sort of reveal to you that it has an interval of convergence. By some kind of a situation like this, the ratio test is really useful for finding this. Right, so you can see here that whenever the absolute value of x minus 2 is less than 1, then the ratio test will tell us that this guy here will converge. Okay. Okay, and so the radius of convergence is 1, right? Is 1, r equals 1. Now how am I getting that? Well, it's centered at 2, right? And this is telling me that x minus 2 has to be less than 1, right? So if I've got 2 here, then I've got, that's the center of my interval. The difference between x has to be within 1, so up top I've got 3, and at the bottom I've got 1, right? So this thing will converge. It'll converge on the interval 1, 3. Okay. All right. Right. So in this example, the radius of convergence is not just a single point, but an infinite number of points. All the points lying in the interval from 1 to 3. Okay. So if we were to plug in a 1.765, for example, just one crazy number that's in here, 1.765, we plug that in for x, the series would converge. If we plug in 2.99999, right, the series would converge. I can plug that in here and calculate this infinite sum, and you could just use the normal test for convergence, and you'd find, in fact, like the ratio test would tell you, that this would converge. Okay, very cool. Right, but then anything outside of that interval would cause the infinite series to diverge to infinity. Right, so if I were to plug in 3.1, f of 3.1, I would get something that diverges. Okay, anything outside of that interval. All right. Very good. Let's do one more example. So let's do an example. We'll find r for f of x equals sum from n equals 0 up to infinity of -1 to the nth power times x to the 2n plus 1 power, all divided by 2n plus 1 factorial. Okay. Right, so we know that if I plug in a 0, we're going to converge at 0 because this series is centered at 0. Okay. So then where else? Do we have an interval that we can look at here? Let's take a look. So we're going to use the ratio test again. So it's the limit as n goes to infinity, and this is going to be a big, well, let's write it out first. It's un plus 1 over un, right? And so our numerator here is the n plus 1 term, and so that's negative 1 to the n plus 1 times x to the, now this is going to actually be 2n plus 3, because remember you got to plug the 2 times n plus 1 and then plus 1. So this will be 2n plus 3, and then divided by 2n plus 3 factorial, and then below that is just basically the nth term here. So negative 1 to the n, and then x to the 2n plus 1 divided by 2n plus 1 factorial. Okay. And then, of course, the way to deal with this is to invert and multiply. So negative 1 to the n plus 1 times x to the 2n plus 3 over 2n plus 3 factorial times, right, and now everything will be flipped upside down, so it'll be 2n plus 1 factorial over negative 1 to the n times x to the 2n plus 1. Okay, so a big kind of messy thing here, but everything kind of cleans up really nicely. Right, so let's kind of segment it out here. What are all the pieces here? Right, so you've got the negative 1 to the n plus 1 over negative 1 to the n, right? Definitely going to get some cancellation there. Then you've got x to the 2n plus 3 over x to the 2n plus 1. You're going to definitely get some cancellation there. And then the factorial as well is 2n plus 1 factorial over 2n plus 3 factorial. Right, so sometimes just like writing these things out like this can be helpful. So this tells you that the limit as n goes to infinity, and what we're looking at now is just a negative 1 times an x squared times a 1 over, now what's left here? It'd be 2n plus 2 times 2n plus 3, wouldn't it? All of the rest of them would cancel away from the given the numerator. Okay. And so let's see here, what's next? We would say limit as n goes to infinity of, and we don't really care about the negative, right? We really don't care about the negative, so let's just drop it. Oh, well, it's the absolute value, I guess, right? So the absolute value would negate it. We also don't care about it, but so then you'd have 2n plus 2 times 2n plus 3. Now what's going to happen to this guy? Well, in this case, you got to think of x as fixed, right? So for any fixed x, if n starts to get larger and larger, then this denominator is going to get larger and larger. It's going to be some finite value divided by some growing value, right? So this is going to be 0. Okay, and this is, again, you have to think about this for any fixed value of x, right? It's going to be 0. So by the ratio test, we would say, what can we conclude? Well, the ratio test, we conclude that the value of x really doesn't matter at all, actually, right? And the series is going to converge for all x, right? So the ratio test would suggest that the series will converge for all x in R, for all real numbers. Right, so this is an example where the domain of the power series is R. So the domain of f is the whole real number line. Okay, and in this case we would also say that the radius of convergence is infinite. Okay, so basically everything. Okay. All right. Excellent. That's great. So we've talked through what a power series is. We talked through how we can think of it as a function. And when we think of it as a function, we have to identify the domain of the power series based on all of the values of x where the power series converges, where the infinite series would converge. And we've said that that can be either a single point, i.e. the center, wherever the center of the power series happens to be, or it can be an interval, or it can be all real numbers. Now, the one thing that's kind of unanswered thus far is, in the case of an interval, what about the endpoints? Okay, so what about the endpoints? So if the radius of convergence is r, right, less than infinity, well, between greater than 0, less than infinity, right? So i.e., we're talking about an interval. If the radius of convergence is, in between here, and the domain is an interval, a finite interval, what about the endpoints? Right, what about those endpoints? Well, yeah, so it turns out that there's no nice, clean answer for this, at least not yet, and that basically the endpoints would have to be tested separately, right? And so for an interval, the domain could be any of the following. It could be c minus r to c plus r. Now here, open interval. It could also be a closed interval, c minus r up to c plus r, right? Meaning the endpoints also produce a convergence, right? It could also be half open, right? So maybe the lower endpoint is outside the domain, but the upper endpoint is inside the domain, or maybe the reverse. All right, so all 4 of these are possible in the case of an interval. Okay. Right, and so let's take a look at an example or two and see how we might test some of these endpoints. Okay, so we've got here's an example. Find the interval of convergence for f of x equals the sum from n equals 1 to infinity of x to the n over n. Okay, so let's first of all, kind of quickly, in the same manner as we have been doing, identify the interval. We'll need to know the interval so that we can understand the endpoint, right? So the limit as n goes to infinity of u sub n plus 1 over u sub n is what we're interested in here. So let's lay in those terms. All right, so the u of n plus 1 would be x to the n plus 1 over n plus 1. And we're going to multiply by the reciprocal here. We're going to take that kind of shortcut. And so u of n would be x to the nth power over n. And so we'll flip it over and multiply. Okay, and so that means we've got the limit as n goes to infinity of, so basically here you've got x to the n plus 1 over x to the n, so this would be n times x over n plus 1. Okay, and so that's equal to the limit as n goes to infinity of, and now what we can do here is we can divide everything by n. Right, so you can kind of think of it like this: n times x over n divided by n over n plus 1 over n, right, absolute value still. This kind of cleans this up and makes it a little easier to interpret. All right, but basically you got x on top, and then down below you've got 1 plus 1 over n. Right, right? And so that means this is going to be equal to basically just, well, so this piece down here will go to 0. This is 1, and that's x, and so we're stuck with just absolute value of x. Right, so that tells us that this converges whenever the absolute value of x is less than 1. Right, so r is equal to 1. Right, so the interval that we're interested in here then is centered at 0 is -1 to +1. So the interval includes at least -1 to 1. Right, now what we need to question next is what about the endpoints? Right, so what about the endpoints? Okay, what about those? So let's start with the upper endpoint. So when x is equal to 1, what happens? Well, let's evaluate the function at 1. So f of 1 would be equal to the sum from n equals 1 up to infinity of 1 to the nth power over n, which is equal to the sum from n equals 1 to infinity of 1 over n, right? So the nth power doesn't matter on a 1. And so this is a, what happens here? This is a divergent power series, or p series, isn't it? This is a divergent p series, right? Because p equals 1 here, right? You can think of a 1 there. All right, and when p equals 1, actually this is a harmonic series, and the thing would diverge. So that means the upper endpoint is out. 1 is not in the domain of f. So what about when x equals -1? Okay. When x equals -1, the series is this. It's f of -1, which is the sum from n equals 1 up to infinity of -1 to the nth power over n. Right, now here, the numerator definitely matters, right? Because this becomes an alternating series. Right, so this is an alternating series. And so the alternating series test, if you recall, two things had to be true. So the first one, we need to confirm convergence. We need, first of all, a of n to be greater than or equal to a of n plus 1. Well, is that true? Well, a of n is basically 1 over n. A of n plus 1 is 1 over n plus 1. Yeah, that works. Check. Got that. Right, the denominator is always going to be larger than the n plus 1 term, so that's good. And now the other thing we need to know is the limit as n goes to infinity of a of n needs to equal 0. And so is that true here? Well, here we have the limit as n goes to infinity of the a of n is just 1 over n. So it's 1 over n. And this definitely converges to 0, doesn't it? 1 is fixed, n is growing. So as n gets larger and larger, this gets closer and closer to 0. Okay, and so check. So by the alternating series test, go to the next page here. By the alternating series test, this converges. Right, and so that means -1 is in the domain of f. Okay, right, so -1 is in the domain of f. And so the interval of convergence is not -1 to 1, but is instead -1 inclusive up to +1 exclusive. So this is a half open interval. All right. So this is the interval of convergence. Of course, r is still 1, right? That additional 1 point at the very end of the lower end of the interval doesn't impact the radius of convergence. But technically speaking, the interval where the convergence takes place does include the lower end point. Okay. All right. We're going to make this a two-parter, so I'll end in the first half of the lecture here, and then in a moment we'll jump into part B, which will be we'll start to talk more about how to represent different functions using power series. All right, so we'll see you all in that part 2 video.